So week 4 may be the most difficult chapter conceptually. We're going to talk about temperature and the controls on global temperature, and then we're going to talk about circulation, ways that the temperature gets evenly or distributed. So there's some basic principles that you need to be able to apply. When we talk about water, we know that water can be available as a liquid, as a solid, or as a gas. And as a gas, it's in water vapor. So it's moisture in the atmosphere. And when we talk about that, we're talking about humidity, so how much moisture the atmosphere can hold. And hold is probably an incorrect term, but it's commonly used in this respect. So relative humidity is the amount of moisture available with respect to the temperature. So in general, we know that warm air can hold more water than cold air. So that you see that if you're, I was just thinking about in taking a shower in the winter, by the mirrors and the windows fog up. In the summer that doesn't happen, and that's because in the summer the warmer air is able to absorb or hold that water vapor. It doesn't condense. The other thing you need to know is that warm air is more buoyant, it tends to rise, and cold air is heavier, denser, it will sink under the weight of gravity. And that's the same with warm water. Warm water is more buoyant and will rise. Warm magma is more buoyant and will rise to the top of the surface. So you need to understand kind of that basic idea. So when we look at temperature, the last couple of weeks we're talking about solar insolation and the input of the sun as it moves with respect to Earth's tilt. And what we know is that it's not just latitude that has an impact on the global temperatures. There's also altitude or elevation. There's a concept called continentality and cloud cover. So you want to be able to discuss all of those with respect to temperature. So when we talk about temperature, we're talking about the transfer of kinetic energy. So warm objects tend to move faster, cold objects move slower, and this is the only diagram I could find, and it's, I don't know, it just shows warm things moving faster than cold things. The book or the reading also talks about two ways that energy can be transferred. Temperature energy can be transferred. We can transfer energy as a diabatic temperature change, which means kind of the direct molecular transfer of energy from one surface to the other. The other is adiabatic temperature change, and this is the change of temperature due to changing atmospheric pressure. So when air expands or goes up in altitude, it expands as the pressure lessens, and as the pressure lessens, the energy is released, and that cools the air. It can also cause condensation in clouds. And so there's a formula that air, let's see, in the reading that explains that a little further on. So when we measure temperature, there are specific protocols for how you measure surface temperature, how far above the surface. There's a standard rate of measurement, and there's 3 different ways that we measure temperature, record temperature. One is using the Fahrenheit scale, the second, which is the Celsius scale, and most of the world's scientific international scale uses Celsius. And then there's the Kelvin scale, and this Kelvin scale is often used for scientific research. And you can look at the diagram and see what is the temperature for freezing of water. With the Fahrenheit scale, it's 32 degrees Fahrenheit. With Celsius, it's 0, and Kelvin, it is 237 Kelvin units. So again, latitude may be the primary control of temperature. So you see this net gain in solar insolation, which gets transferred into temperature along the equator, and a net loss on the poles. So if there wasn't a way to transfer or move that temperature, it would get exceedingly hot at the equator and a much less heat at the poles. So one of the controls is altitude or elevation. We talked about adiabatic temperature change, and we consider what is considered the normal lapse rate, so that air temperature loses about 3.5 degrees Fahrenheit for every 1,000 feet in elevation. And so there is an example in the reading of how much elevation you would lose as you go up over specific heights. So for example, if I'm let's see, if I'm in Oregon, starting at an elevation of 450 feet above sea level and the temperature is 75 degrees Fahrenheit, and I go to the top of the South Sister, which is at 10,358 feet, I'm able to calculate what that rate would be, and that would be a great exam question for you. So here's an example of two places that are at very similar latitudes, however their elevations are dramatically different, and you can see that in Japan the average temperature at Mount Fuji is much colder than in Newton Grove, North Carolina, and that's a result of that control of altitude. Another control on temperature is cloud cover. So this is probably the most variable aspect. It's hard to kind of predict where clouds are going to be over the long term, and they move from spot to spot. And so as we talked about in earlier chapters, clouds block that incoming solar radiation so they can reduce temperature, but they also can block outgoing radiation, which would create sort of a blanket effect and keep the earth or the area warmer. And you guys know this, on a cold, clear night when you can see the stars, it's much colder than on a night where you've got some cloud cover. The other control is continentality, and this is basically related to the fact that land surfaces heat and cool quickly, but water does not heat and cool that quickly because of the mixing ability of water and the water's high specific heat. And so if I'm going to heat the surface of the water, that's going to set up a convection current, and it will take a very, very long time for the water to heat up. And so this means that land that is close to water is influenced by that water, and land, say in the middle of the country, would heat and cool quickly. So here is an example of two locations, both at about, let's move this little picture down here. Let's see. I'm looking at, yeah, this Portland, Oregon is at 122 degrees west longitude, and Bangor, Maine is at 47 degrees west longitude. They're at about the same latitude, but Portland has a much warmer average temperature in January than Bangor, Maine, because Portland is the warm energy from the ocean has a modifying effect on the temperature. If we were to look at a mid-continental temperature, it would be even more dramatic than Bangor, Maine. So the reading takes you through just kind of general discussions of the latitudinal and the longitudinal aspects. So I would like you to be able to generalize temperature patterns north to south. So looking at the equator being warmer, the poles being cooler in general. Let's see. And then being able to look at the longitudinal patterns where you have areas that are modified by warm oceans. So make sure you read through that section in the readings. I think it's pages page 5 and 6 in the text. Also, it has a nice explanation of places that are along the west coast to the middle of the country to the east coast, and you can look at those temperature comparisons that really show the difference between the continentality that is impacting San Francisco, the middle of the country in Dodge City, Kansas, which has like a -4 degrees centigrade, and then Atlantic City. So make sure you look at both of those. The other thing the reading talks about are general temperature trends. And there's how do we know what the long-term temperature is, and how do we know what is maybe caused the long-term cooling and heating? Well, one of the ways is through information from ice cores. By drilling down into glacial ice, scientists are able to take slices out of those ice cores and find the concentrations of gases. They're also able to date those ice cores by different things like volcanic ash falls. Scientists also look at ocean core sediments in deep oceans where the bottom of the ocean is not mixing, and being able to look at the makeup of those ocean cores, they're able to understand how cold or how warm the ocean was at different periods over time. So take a look at that ice core example, because I know there's a couple questions related to that. And then they talk about just these overall regional patterns. How do we think that areas are going to change? And what you'll notice is we don't call it global warming anymore, because some places are going to get warmer, some are wetter, some are colder, and the current term for this is global climate change. So make sure you can kind of talk about the mid-latitudes, the subtropics, and the tropics. That's also I think in page 8 and 9 in the reading. What's going to happen in those areas? What's going to happen to rainfall? What's going to happen to temperature? What is going to be the response to crops and food growth? Those kinds of things. And then finally, a little bit about closer to home. If you're from Oregon, what is the prediction for climate change in Oregon? Well, one is that we are going to have less snow in our snowpack, and the snowpack actually contributes to streams in the summer. So with less snowpack, we may have some stream flow issues. There's going to be competition for water between farmers and urban areas. Higher temperatures means there could be increased pesticides. There could be much more vegetation in the forest, which could lead to greater and more frequent wildfires. And what they're predicting is that snowfall may end up later in the year, so that it won't be very cold. It won't be able to keep that snow, but we may get more rain and more flooding. So lots of different changes in when rain happens, how much rain we get just in this state. So a lot of stuff to think about. I think if you focus on trying to understand the things I went over here, for the most part, you will have a good coverage of this part of the lecture.